Okay, our next class, we're going to do calculations with acceleration. Now, by definition, as we've seen, acceleration is the velocity change per second. So, if you want to find the velocity, then you can first find the change in velocity by multiplying acceleration by elapsed time. And then that'll be the velocity change, so you would add what the initial velocity was to the change in order to find the final. So this is the first constant acceleration equation. This is how we calculate velocity when we're accelerating. Now, for finding the displacement or the location of an object when we're accelerating, we can't use this relationship, d is vt, because that's only true if you're moving at constant speed. Well, we can, however, use our definition of average velocity, because that works everywhere. Average velocity was displacement over time. And we can just cross multiply and say, okay, displacement's average velocity times time. And then it turns out that average velocity when we're accelerating is the sum of the initial and final over 2, again, multiplied by the elapsed time. Sorry, I should have a delta t here. Okay, so that's how to calculate velocities and displacements when we're accelerating. Let's do our first simple example. So we've got an object starting at rest. There's a picture at the bottom there. And it accelerates at this rate, 2 meters per second. And the acceleration is to the right, so it's being pushed to the right, going faster and faster. So let's find its velocity and position. Okay, so we'll just use the conceptual definition of an acceleration, a velocity increase of 2 meters per second each second. So if we start at rest, that's a velocity of 0, and then each second we just gain 2. So we're going faster and faster and faster. Now, these numbers are exactly what you would get if you calculated using that first relationship we just wrote down. Vf is Vi plus a t, or a delta t. For instance, with an initial velocity of 0, acceleration of 2, and a time of 3, you get 6. Okay, now we know how fast the object's going. Let's see where it's located. So, we know that a displacement is an average velocity times a time. And we know that an average velocity is just the sum of the initial and final over 2. So we have to be careful about which time interval we're looking at, and these time intervals we've specified, so we're always referring very back to the beginning. So between 0 and 1, the average velocity is just the average of 0 and 2, which is 1 meter per second. Now that's a time interval of 1 second, right? So if you're doing an average of 1 meter per second for a second, that is 1 meter of displacement. So we went over 1 meter, located right there. Okay, from 0 to 2 seconds, that's an elapsed time of 2. So we're now averaging these two velocities. So we were going on average 2 meters per second in that interval. And it's a 2 second long time interval, so we traveled 4 meters. So from the start, at the 2 second time, we are now up here at 4 meters. Between 0 and 3 seconds, we're averaging these two velocities, 0 and 6. We're going on average 3 meters per second. And so we have traveled 9 meters from the start, so we're now out here at the time of 3. And we could just make a graph of that motion. Now notice we're not getting the same uniform spacing that we were for uniform motion. Just switch the slide. At 1 second, we're at 1 meter. So notice the scaling. This is 10, 8, 6, 4, 2. This is 2. So 1's right here. At 2 seconds, we're at the 4 meter mark. At 3 seconds, we're at the 9 meter mark. This is not a straight line. It's actually a curve. It's actually parabolic. as we'll see shortly. There we go. The velocities, however, increase at a uniform rate. 5, 4, 3, 2, 1. At 0 seconds, we were at rest. At 1 second, we're traveling at 2 meters per second. At 2 seconds, we're at 4 meters per second. And so on and so on and so on. So the velocity is just going up by 2 meters per second each second. And the acceleration is the slope of that velocity graph. So this is just connecting the graphical analysis of motion with the sort of numerical, mathematical calculation analysis of motion. So we have two results so far to find velocity and displacement. It turns out there's a couple of other self-consistent relationships between these quantities. Here's another displacement equation, another way to find displacement. And then this equation relates acceleration, displacement, final, and initial velocity. Now, there's a lot of, I should really go back and put the vector signs on those previous equations because these are vectors, right? So direction matters for these things. So that's a vector equation, sorry. And so is this one, displacement and average velocity. So all these things are vectors. See, I even had the vector signs there to remind myself and I still forgot. The good news though, however, is that as long as there's no direction changes to be concerned about, and as long as we're just going in a nice straight line, we could just drop the vector signs. We can also drop the delta t and just write t, as long as you remember that it really means an elapsed time. And then these equations, they look a lot neater and tidier already. So these are the 4 constant acceleration equations. Let's do a quick example. So we've got an object starting at rest. Okay, so we visualize. So that's a terrible drawing. All right. An object starting at rest. Here, we'll use the line drawing tool. Isn't that nice? And so starting at rest, rest means initial velocity is 0. If you start at rest, it travels 12 meters. Okay, so that tells us the displacement's 12 meters over the next 3 seconds. So delta t, the elapsed time, is 3 seconds while accelerating constantly. Okay, so here we are over here. We're accelerating, so we've picked up speed. We don't know what the final velocity is. We also don't know what the acceleration is. So how will we go about finding that? So we know initial velocity, displacement, and time. So we look at the constant acceleration equations and we kind of do a mental accounting. So we know initial velocity and time. So there's 2 unknowns in that equation. That's not useful. We know the distance and the time and the initial velocity. Oh, that would work. We could use this relationship to find the final velocity. But we were looking for the acceleration. Let's see. So we know distance, initial velocity, and time. Here we go. This one will work for finding the acceleration because there's only one unknown. And if you memorize the equations, you'll get very good at that process of figuring out which one to use. So good structured problem solving will specify the task. We're trying to find the acceleration. So we write out the displacement equation. D is VIT plus half VT squared. Substitute in the displacement. Now, you'll notice that I'm not substituting in the units because the units will work as long as you use consistent units of meters and seconds. Then you don't need to plug them in and do the algebra. But if you do the algebra, it will work out. 0 times 3 is just 0. So on this side we have 12. On this side we have a half times a times 3 squared, which is 9 over 2, or 4.5 times a. So we just divide both sides by 4.5, and then we get, for the acceleration in meters per second squared units, the answer. And we see it's 2.6 repeating meters per second squared. Now we've got lots of options for finding the final speed. For instance, we could use the first equation we wrote down today. So the final speed's the unknown, the initial is 0. This is 2.6 repeating for 3 seconds. It's helpful to keep all those digits in your calculator because then you get to see that the answer is actually 8 instead of some rounded off version of that. And so now we can just draw a conclusion, just put a nice box around it. There's the acceleration of the object, and here is its final speed. Okie dokie. Now, not all questions will be this easy. In class, we'll do one that's quite a bit harder. It'll be another one of these interception problems where you want to know when two objects meet. So you have to be quite organized with those. But we'll start with a simple one, then do some average ones, then move up to this hard one in class together. But we're not quite done yet, because another topic for today is a special type of acceleration. It's the freefall acceleration. When an object is dropped and air resistance is insignificant, we say it is in freefall. Now, I should be careful. I said when it's dropped. You can actually throw the object upwards, and that's still freefall. It still has the same acceleration. So the main thing is that gravity is the only force acting on the object. So it's moving on its own through the air, and air resistance is not significant. That's what freefall is. Now, some things we need to know about objects in freefall. If it's going straight up and straight down, then at the top it stops momentarily. When it comes back to the launch elevation, then the velocity at that point is just the opposite of what it was launched at. The displacement, which is the change in position, is actually zero because there's no change relative to where it started. And the amount of time it takes to come back to the launch is just twice the time it took to get to the top, since rising and falling are symmetric. Now, if we do happen to be sort of launching this and having it land, say we lean our hand out over the edge of the building and have it land below, then the displacement just before it hits the ground, so the change between here and here, is exactly the height of the building or the cliff. However, it is downwards, so that's a negative displacement. So if this was a 30-meter high cliff, your displacement from the launch to the ground would be negative 30. Now, really, what we're going to do here calculation-wise is just the same as the problems we were working on earlier. We're just going to use the constant acceleration equations armed with that list of facts we just put together. So here we're throwing a projectile. It leaves the thrower's hands at 10 meters per second. So that would be the initial launch velocity. And it's upwards. And so as a vector, that will be upwards 10 or positive 10. How long does it take to reach the top? So at the top, we know it stops momentarily. So that'll have a final velocity of 0. Now, our acceleration is 9.8 meters per second squared downwards. So as a vector, that's negative 9.8 meters per second squared. Okay, so we want to know how long does it take for that to happen. That means we want to find time. So the first kinematics equation will work wonderfully. Our final velocity is 0. Our launch speed was 10. Our acceleration is downwards 9.8. This is an equation that we can solve for time. Mathematically, the easiest thing to do is going to be to take this negative 9.8t over to this side, where it becomes positive. And mathematically, to solve for t now, we just divide both sides by 9.8. It will be in seconds units, and we see it's 1.02 seconds. I'll just build that result into a concluding statement. And there you have it. Now again, this is a fairly straightforward question. In class, we'll do one that's a little bit harder, and then you'll work on some easy ones, and then we'll do a hard one, just to make sure that we really have mastered this concept. So that's it for next class, constant acceleration equations.